we're already almost halfway through our discussion, in fact beyond halfway, and the point at which we finished off the previous lecture is the following. If we have some unitary operation that we represent as uq, and we have n qubits that are coming into the system, and we started off our discussion by looking at what uq does to an input state ket j, which is really an n-dimensional, 2n-dimensional n-qubit state, a sequence of j1s, j2s, j3s, where each of these j's is either a 0 or 1. So if this state is fed in to the circuit or the propagator for the quantum Fourier transform, we get a certain output. And that output, we already calculated the output, and it was given by 1 over 2 raised to power n square root ket 0 plus ei 2 pi j 2 minus 1 ket 1 crossed with, so this is what the first qubit is going to look like. Second qubit is going to look like the following: 2 pi j 2 raised to power minus 2 ket 1, and so on till you reach the bit n. I 2 pi j 2 minus n ket 1. This is what the output is going to look like. Now the output is a separable state given the input is this ket j. Ket j, so this is the input state expressed in integer form, and this is the same input state expressed in its binary string form as a sequence of zeros and ones. And we already know what the relationship between j's and these j sub something are. The relationship is given by this j, which is an integer, is jl 2 raised to power n minus l, where this l goes from 1 to n. So this is how you can convert any string of zeros and ones to its equivalent integer form. Correct? Can you please test this out? For example, if my j is 0, 1, 0, and we're looking at 3 qubits, my n is equal to 3. What is small j here? 2, right? So the integer form of this binary string is the number 2. So this is really equal to ket 2, and so on. So through a very lengthy but a systematic calculation that we did in the previous lecture, this is what the output looks like after we feed the quantum Fourier transform circuit with an input which is a nice clean binary string. Can you check your notes from the previous lecture if I've written this down correctly? Please, this was the last sentence I wrote.
नॉर्मलाइजेशन कांस्टेंट नहीं था, I think so.
क्या था?
नॉर्मलाइजिंग कांस्टेंट
वो ये नहीं, capital N. The capital N is the same as 2 raised to power n. So capital N is the same as this. Now the question is, okay, this is all looking very nice mathematically. So we are inputting a state, and just let's look at this from an intuitive perspective. What are the output qubits looking like? First of all, for this nice computational input. It's not a superposition, but it's a computational input. Each one of these qubits remains separable. And so this is a point on the block sphere. This is another point on the block sphere. Another point on the block sphere. Correct? So if I just look at the block sphere, so I can use this block sphere description because all the qubits are separable. So I can use n 1 qubit representations. Otherwise I wouldn't be able to look at the block sphere. So if I look at a single block sphere and I look at a point on the equatorial plane, so if I focus just on the equatorial plane and I look at a point here, some angle phi, then all of these points are going to be represented by 1 over under root 2 ket 0 plus e I phi ket 1. Right? So you change phi, you get a different point of the equatorial plane. And if you look at each of these output qubits, each one of them, if I were to draw a block sphere corresponding to each of these qubits, so I just draw the equatorial plane. J is some number, which is the decimal equivalent of the input, the binary input here. I am dividing that J by 2, halving it, dividing it by 4, dividing it by 8, dividing it by 16, dividing it by all the way up to 2 raised to the power n. So I have some phase here, depending on J. The next state will be some fraction, so I will half this phase. The next will be half of this. The next will be half of this, and so on. So I'm getting successive phases, and each one of these phases is gotten from the previous phase by dividing by 2. Alright? So this is intuitively what is happening, what the quantum Fourier transform is really doing. Okay? Provided you input this with a binary string. Now the question, oh, this is all looking so nice mathematically, fine, very nice, clapping. But how do we implement this in our hardware? So we need to draw a circuit for this. And we have quantum gates, and so how does this translate into a circuit model? What kind of circuit do we need to build? So in order to do the circuit description of the quantum Fourier transform, we'll have to massage the algebra a little bit. Remember that our J is given by this JL 2 raised to power n minus L. So if I look at the first term, in the first qubit, J 2 raised to power into 2 raised to power minus 1. So I'm really doing the following: JL 2 raised to power n minus L minus 1. J, the next term, is going to be further subdivide this by another factor of 2. And so on, right? So the last term is J 2 raised to power minus n is JL 2 raised to power minus L minus n. Do you understand what this is? So I'm just multiplying this with 2 raised to power minus 1 because I have this term over here, then I have this term over here. So just trying to see what this looks like.
You are just bringing them out of that.
Yeah, I'm just trying to express this factor, which is in the second qubit, as a sum. Then I'm looking at the next factor and expressing it as a sum. Okay, so I'm just trying to come up with a simple mathematical description, and you recognize what's going to happen. All right. So if I were to look at this term, this is really if I were to expand this, what does this mean? Let me expand this. Let me break up the sigma sign for this term and see what's going to happen. J1, 2 raised to power n minus 1 minus 1 plus J2, 2 raised to power n minus 2 minus 1 plus J3, 2 raised to power n minus 3 minus 1 all the way up to Jn, 2 raised to power n minus 1. Right? Now, I know that this definition is true. This is how I convert a binary sequence, JLs, into an integer. If you remember from our last lecture, from our previous lecture, we also had another definition in front of us. So let me move to this piece of the blackboard. If I were to write 0 dotted with Jm, say some m, this really means this is a notation to express this thing, Jm 2 raised to power minus 1. So I just take this number 0 or 1 and divide it by 2, and I get an integer, a fractional integer representation of Jm. So, for example, if I have 1 into 2 raised to power minus 1, this is 1/2. This is represented as the binary fraction 0.1. So this is just a piece of notation that represents this thing. Alright? For example, I know that the example that I looked at, if I have j equals 2 in integer form, this really means 0, 1, 0 in binary form. If I took this j and already. If I took this j and multiply it, for example, with 2 raised to power minus 2, so this is, so I don't multiply, okay, let me just multiply, put a multiply. This is 2 over 4, this is 1/2, right? This is all in integer form. So I'm treating j as an integer. But what does this thing look like in binary form? This is going to look like 0.1, because if I were to divide by just 1, 2, there's a decimal place here, shifts 1 position, dividing by another factor of 2 shifts the decimal point here. So this is the philosophy behind this notation. This thing really is 0, 1, 0, 0.000 and so on. So when I divide by 2 in binary form, this decimal shifts to the left 1 point. I divide by another factor of 2, it shifts leftwards. So each division by a factor of 2 is going to hop this decimal point from one position to the next position in left. Alright, so this is just a notation. For example, let's look at some examples. 0.1. This is 1 into 2 raised to power minus 1. 1/2. 0.11. This is 1 into 2 raised to power minus 1 plus 1 into 2 raised to power minus 2. This is 1/2 plus 1/4. So when I have this number in decimal form, it really means in binary form you would like to express this as 0.11. Alright? So remember, this is just a definition here. If I had 0.jm, jm plus 1, jm plus 2, and so on, jm plus r, this would really mean that I'm taking the j's, jl's, and multiplying this with a factor, and that factor is given by minus m minus l, where l goes, sorry, minus 2 minus l, minus 1 minus l, sorry, where l goes from 0 to, I think, r minus 1, I think so. So this is our definition. So let's use this definition and try to tidy up a few things over here.
L plus j L plus m होगा subscript.
किधर?
Subscript में j L plus m होगा. Because m.
Oh, sorry. ठीक. इसको मैंने let's write this down properly. This is Jm, Jm plus 1. This is really equal to Jm 2 raised power minus 1 plus Jm plus 1 2 raised power minus 2 plus the next term Jm plus 2 2 raised power minus 3 all the way up to the last term Jm plus r 2 raised power minus r plus 1 is minus r. That's right, in this fashion. Okay, so I can now generalize this. This is going to be equal to Jm plus l 2 raised power minus l plus 1, where l goes from 0 to r. Okay, this is the formula. So the first position to the right of this decimal point means that you're dividing the number by 1/2. You're halving the number, dividing by 2. The second position to the right of the decimal means you're dividing by 4. The next by 8, and so on. Now let's look what's happening over here. This thing is, if this minus 1 didn't exist, this minus 1 didn't exist, this minus 2 didn't exist, this minus 3 didn't exist, we just had j, right? So if there were no 2 raised power minus 1, this term wouldn't exist, right? Now we're dividing this entire sequence of j, which is given by this thing, by, this is being divided, everything is being divided by a factor of 2. Correct? Because here's what we're doing. We have j in its pristine form. In its pristine form, this is what j is. Now when you multiply by 2 raised power minus 1 or divide j by 2, you put another half, you are halving each one of these terms. And when you are halving each one of these terms, the entire sequence of j shifts in a manner that the decimal place from here hops to the left by 1 unit. So this thing really is, this thing is j1, j2, j3, all the way up to jn minus 1 dot jn. Correct? Got it? So without this factor of 2 raised to minus 1, you would just have this sequence here without the decimal. Now you have put this decimal in, the entire sequence is being divided by 2. That means you take the decimal and shift it by 1 position. This term likewise is in its binary form is going to look like the following: Jn minus 2 dot Jn minus 1 Jn. Correct? And so on. This term J1, J2, J3. I think so. Jn minus L, Jn minus L plus 1 up to Jn, and so on. So now let's write this sequence in its fractional form. Okay, now we know what the notation looks like. Let's write the sequence that we have at the top in its fractional form. And from that, try to motivate what kind of circuit are we getting. Are you getting all of this? Yes? Please?
Sir, if we have a 4-qubit state, and for example we have 0, 1, 0, 1 and 0, 1, 1, 0. So like if I then find out the numbers for the binary form, so they turn out to be the same using this formula, I guess. How do I distinguish?
So let's look at this. So I have n equals 4 and one of my j's is the following. This is 0, 1, 0, 1. Right? So this is the number 4. Let's choose another number.
0, 1,
0,
1, 1,
1.
1, 0.
This is the number 5. Sorry, this is the number 6.
6, 1.
Right. So now what would you like to do? You would like to take the number J4 and divide by 2. Okay. So what are you trying to do here is to take the number 4, divide by 2, is you would get 4 over 2, which is 2. So here you have 6 divided by 2, this is 3. So these numbers are different. Alright, so
what does this 2 and 3 mean?
So this is just an integer representation of this state.
What is this 2 and 3? What do
These two numbers.
the final answers 2 and 3?
So I'm just answering your question that these binary representations, she thought that they would have the same integer representation, but they don't. They have different integer representations, 4 and 6.
Why are we calculating the next 2 steps, 2 and 3?
So, so what we're trying to do here is I really don't know what we're trying to do here. So have I answered your question?
Yeah, I thought the same idea but they're different.
Right, so that's it, that's it. So let's look at the prescription over there. UQ acting on J is now equal to 1 over 2 raised to power n square root or capital N square root. Let's look at the first qubit, cat 0 plus E I 2 pi. And the first term is J divided by 2. J divided by 2 is this thing over here. Correct? So instead of J divided by 2, I can write 0 dot J1, J2, J3, sorry, J1, J2, J3, Jn minus 1, dotted with Jn, get 1. This is my first term. Is that correct? Why are you so confused? Isn't this correct? What I've just picked this thing and put it over there. The next term is tensored with get 0 plus e I 2 pi j1 j2 jn minus 2 dotted with dot jn minus 1 jn, get 1. Yes.
So when we write something like जैसे वहाँ पे j times 2 raised to the power of minus something, so that is just notational significance. That doesn't mean you're dividing j by 2. That doesn't mean that.
This thing?
Yes.
No, this is in decimal, it's real. So if you have a number 4 or a number 6 or a number 3, this j represents some integer. So now you are multiplying that integer by 2 raised to the minus 1, right? Because this is a phase. This is just some number here, some phase here. 2 times pi times an integer divided by 2, or pi j I pi j. This is I pi j, right? It's really dividing this thing by 2. So it's real. It's not notation. And so there are two ways of representing states. One is by writing a decimal or an integer j. The other is writing this as a sequence of small j's with a subscript. And each one of these subscripts can be 0 or 1. So this is a binary representation, whereas this is an integer representation.
So, like if you multiply, let's say 4 by 2 raised to the power of negative, and you get 2. So, uski binary representation, we know what that is. But according to these definitions over here, uski binary representation should just be 0, 1, 0.1, which is not the binary representation.
Right. So there is no such thing as, so when you introduce this notation here, this notation, this is not, this now is a real notation. It's not a real number. This is a notation to represent this thing over here. This is real. This thing is real. This is an integer. But this, when you divide by, when you use this decimal point, that becomes a notation.
सर
Yes.
सर वो जो 4 आपने लिया वहाँ पे कैट 4 सर वहाँ 5 नहीं होना चाहिए
चलो 5 कर लो.
सर जो आपने स्टेप किया वो भी 2 और 3 आंसर्स आए थे मैं काफी वो इंटीजर से ही इंटीजर पे जाने की कोशिश की थी जबकि वो बाइनरी से इंटीजर नोटेशन इसीलिए वो चेक कर रहे थे.
ठीक है. So now we keep on this operation 0 plus ei 2 pi j1 j2 jn minus 3 and so on. Finally, we'll have ei 2 pi dot j1 j2 Now there is another simplification that can be done. So this factor here, represents a true integer. This factor here represents a true integer. So this is a sequence of zeros and ones before the decimal point, before this point. Let's not call it a decimal point. Before this point, this is a true integer, right? This is also a true integer. A true integer. And what's beyond the decimal point, you're taking those values, those zeros and ones, and dividing by 2, dividing by 4, dividing by 8. So if you look at the exponent of an integer, ei 2 pi, some integer here, say p. So what is this equal to?
Cos 2 pi 5.
So what is this equal to?
0 on the side. जो final आपने expression लिखा उसमें 0 नीचे कॉम्पोनेंट
0 कहाँ से आया? क्योंकि all the decimal has shifted all the way up to this point. So what is this equal to? What is this factor equal to? P is an integer.
1.
1. This is factor is equal to 1. So 1 doesn't really matter. So you can simplify this further as 1 over 2 raised to the power n, 0 plus ei 2 pi j n ket 1, 0 plus ei 2 pi j dot 0 dot, you can put a 0 here as well if you like, 0 dot j n minus 1 j n ket 1 times so on all the way up to ket 0 plus ei 2 pi 0 j1 j2 j3 all the way up to jn ket 1. So what I've done is I've taken this integer part out because it's immaterial. This integer part is immaterial because you exponent anything to the power of I 2 pi in integer just turns out to be 1. So you just have to take into account the string that remains after this point. Alright, so when we move on to this, we continue our discussion over here. This is what the quantum Fourier transform really does. It takes an input state ket j, which is really a sequence of j1, j2, j3 and so on up to jn, and out of this it creates a combination, a tensor product of states which are given in the following form. The first qubit becomes a superposition of 0 and 1, and the phase that comes up with the ket 1 goes as I 2 pi 0 dot with 0 dotted jn ket 1 0 plus ei 2 pi 0 dotted jn minus 1 jn ket 1 tensored with ket 0 plus ei 2 pi 0 dotted with jn minus 2 jn minus 1 jn ket 1 and so on. Ket 0 plus ei 2 pi 0 dotted with j1, j2, j3 all the way up to jn ket 1. Fine? So this is the action of the quantum Fourier transform. So what is really happening here? What kind of circuit do we require to build this thing? Hadamard, it requires Hadamard and phase gate. So what's the phase? What kind of phase gates are needed? The phase gates, the phase operation is only occurring with ket 1. So it's like a control phase. The other thing is that the phases are different. This phase is large. This is a finer correction to the phase. This is an even finer correction to the phase because you're putting in more digits after the dot, which means you're successively dividing by bigger and bigger numbers. Dividing the first position after the dot represents you dividing by 2, The second position shows you dividing by 4, then by 8, then by 16. So you're making finer and finer adjustments to your phase as you go along. So now let's come up with a circuit. Let's propose a circuit that implements this. Alright, so let's focus on 3 qubits. And I think most of the questions and confusions will get clear. Just have 3 qubits and we want to find out the quantum Fourier transform of this. Okay, so let me first draw the circuit and see if all of this notation is going to start making sense all of a sudden. Okay, so let's see what's happening. So I put a Hadamard gate here on the first qubit. This is my J1, this is my J2, this is my J3. Each one of these channels could be 0 or 1. Then I apply a gate. I'll define what this gate is in a minute. R2. R3. Okay, and then let's move on. So we've done one part of the story. Let's move here. Let's put a Hadamard gate here, followed by this strange kind of gate. Okay. Followed by a Hadamard gate. So we're dealing with 3 qubits at the moment. Now let's see what's going to happen. So first of all, everyone knows what the Hadamard gate does. Everyone knows that. Okay, so we don't need to go into that. And what this gate does, this is a controlled rotation. Instead of controlled NOT gate, it's a controlled rotation. So first of all, I would like to ask you whether this is a 1 qubit gate or a 2 qubit gate. It's a 2 qubit gate, a genuine 2 qubit gate. Because this is its control line, this is the target line. So what this gate does, so suppose for ease of understanding, I put it like this. So R sum K. This is my first control qubit, this is my target qubit. What this gate does is that if the control qubit is in a state cat 0, it does nothing here. And if this is in a state cat 1, it applies a rotation to this qubit. And what kind of rotation does it apply? First of all, I would like to write this gate in outer product form. First qubit in cat 0 form, I write the cat bra, the operator corresponding to the first qubit being in the state cat 0. When this is the case, nothing happens to the second qubit. So identity on the second qubit. The other possibility is that if the control qubit is in the state 1, then what happens to the second qubit is that I apply a rotation on the second qubit. And the rotation is such that a phase is added, which really means that I apply this gate 1, 0, 0, E, I, 2 pi over 2 raised power k. So what does this gate do alone? This single qubit gate. Now this is a single qubit gate. This single qubit gate alone, when acting alone, takes cat 0 and keeps it as it is, and it takes cat 1 and applies a phase to it, E I 2 pi over 2 raised power k, cat 1.
So ये outer product orientation आप इसको बोलें इसमें.
अच्छा भी कर लो. On its own, this is what this gate does. So let's first look at this gate. What kind of gate is this? It has nothing to cat 0 and it takes cat 1 and adds a phase to it. So it's like a phase gate. So if you remember when we discussed a phase gate, what does a phase gate do? A phase gate does nothing to cat 0 and it adds EI phi to cat 1. This is what the truth table for a phase. This is really a phase gate. a phase gate, but it's controlled by another qubit. So this is a phase gate on the first qubit controlled by the second qubit. Phase gate on the first qubit controlled by the third qubit. Now the phase is such that this is a phase gate with the rotation ei 2 pi divided by 4, 2 raised to power 2. This is ei 2 pi divided by 8. Successively smaller and smaller phases. Alright? So now I'll describe what this gate really does. It's a controlled phase gate. And the phase is such that it's a fraction of 2 pi, and that fraction is obtained by dividing by some power of 2. So you have 2 pi, you divide it by 4, you divide it by 8, divide it by 16, and so on. So you have 2 pi, or you can have pi, or you can have pi by 2, or pi by 4, or pi by 8, and so on.
So that k is representing the number of qubits?
No, that's k is representing this factor here, 2 raised to power k.
Yes, sir. Like if it is controlled by third qubit,
So now let's come to the outer product thing. So that will answer your question. So if I have this thing here, say some rotation u, forget about r's for a minute. Suppose this is the kind of 3-qubit scenario I have, in which I'm putting a rotation on the third qubit, some operation on the third qubit controlled by the first qubit, unaware of what's at the second qubit. Of course, this is an operator. It's going to be an 8 by 8 dimensional matrix. It's going to be large matrix, right? So how can I write this matrix? So I can write any operator through outer products. So the way in which I can write this outer product is that if the first qubit is in ket 0 state, nothing happens to the third qubit. First qubit in ket 0 state, what happens to the second qubit? Nothing. I really don't care about the second qubit. So this is the first position, so we have to agree on the positioning. This is my first topmost qubit, the topmost line. This is this middle line, the second qubit. I have to agree upon some ordering, right? The computer program, you do this on a computer program, you have to agree on that. And if this is the case, that the first qubit is in the state ket 0, now I cannot use kets here because kets is a vector, is a ket. I really need to have an operator here. So what's the operator corresponding to ket 0? It's like a projection operator. It's ket 0 bra 0. Okay? Am I answering your question? Okay. And the third is, when this is the case, nothing happens to the third qubit as well. But there are two possibilities for the first qubit. It could be ket 0 or it could be ket 1, right? These are the only two possible states. We're talking about the computational basis. We are casting everything in the computational basis. We're going to write the matrix in the computational basis or the Zeeman basis. If this were the case, still nothing happens to the second qubit. But the third qubit gets some gate which is u. Generally it's u. Okay? So this is the outer product formalism. Now with this quantum circuit for the 3-qubit state, let's see what's going to happen. Let's see what's happening. So I input a state ket J1, J2, J3. Isn't this some J? This is some J, ket J, which I have now expanded in binary form as J1, J2, J3. Now after the first Hadamard, so let me just do the first Hadamard, UH1, the first thing on. Now this is only on the first qubit. It's not going to change the second and third qubits. So really nothing is going to happen to the second and the third qubits. Correct? But the first qubit is going to change. Now how is the first qubit going to change? What should I write for the first qubit? My answer should have some J1 in it. Can you give you some time to think about it? What should I write for the first qubit? Get 0 plus get 1 or something else? Huh? ठीक है, तो क्या लिखूं? Can I come with a general form? First of all, 1 over n root 2. So okay, let me give you hints. Get 0 here and get 1 here. What should I write over here? Shabash. Minus 1 raised to power j1. Now is minus 1 raised to power j1, can I write this in a cunning form? Minus 1 raised to power j1. So if I am slightly being cunning here, which everyone can, I 2 pi and then I could put this as J1. Over 2. Is that possible?
Sir, they got the binary number.
8 minutes. एक मिनट Right. So J1 is 0 or 1. If J1 is 0, this is 1. If J1 is 1, this is minus 1. So if I were to write this as an exponential factor, I know that my exponent could be something. So it could be minus 1. I do know the following. I do know that EI 2 pi over 2 is EI pi, which is minus 1. I do know this. And I also know that EI 2 pi EI 2 pi over 2 dotted with multiplied with 0 is plus 1, right? So this is EI 2 pi multiplied by 1 over 2. So this is EI 2 pi 1 over 2, this is EI 2 pi into 0 over 2. So half 1 over 2 and 0 over 2. This is number 1 divided by 2, this is number 0 divided by 2. J1 can be 0 or 1. And I am dividing that by 2, which means the general form of this thing is 0 dot J1. This is J1 divided by 2. So what I am trying to do here, in the next step, I am going to put this as ket 0 plus EI 2 pi 0 dotted with J1 ket 1 J2 J3. So I have done my first Hadamard. Correct? Let's do the second sequence. Let's do this controlled gate over here. Yes, please. Huh? So what I could do is, instead of explaining this over, let me see whether this makes sense or not. Okay? Let's look at what this thing is here. What this notation means. This notation means the following. 0 dot with J1 is J1 2 raised to power minus 1. Now this is a pure number. This isn't. This is a notation. But this is a number. Okay, this notation represents this number. Now if I had 0 dotted with 1, so J1 can be 1 or 0. If this were 1, then I would have 2 to the power minus 1, which is 1/2. If this were 0, we would just have 0. Now this is in an exponential factor, 2 pi 0 dotted with J1. So I can either get 1/2 here or 0 here. So there are two possibilities, EI 2 pi 1/2 or EI 2 pi into 0. This possibility arises when J equals 1, and this possibility arises when J1 equals 0. This thing equals EI pi, which is minus 1, whereas this thing equals EI 0, which is plus 1. This thing does explain this, right? So now what we would like to do is we would like to apply the second operator, the controlled R2 gate, the controlled rotation operator. Now what the controlled rotation operator does is that if J2 is in the state 0, nothing is going to happen to the first qubit. If this state J2 is 1, what's going to happen to the first qubit? The first qubit is already in a superposition. Nothing is going to happen to this thing because that's how we've defined our phase shift. However, an additional phase factor is going to be built up here. And what is that phase factor? E raised to I 2 pi divided by 2 power 2, because this is an R2 gate. So E raised to I 2 pi raised to power divided by 4. But 4 is, if you divide by 4, it means you are putting something at the second location after the decimal. Right? If you divide by 8, you're putting it at the third location after this point. So, and what's going to happen to the second qubit? Nothing, just remain J2. So the phase is being kicked into the first qubit. So after this, at this stage, after the first controlled R2 gate, my qubit is going to look like the following. So I've already tried my first Hadamard. Now I'm going to apply the controlled R2 gate on the first qubit. I'm going to get 1 over under root 2, 0 plus EI 2 pi 0 dot J1 from the first operation. Nothing is going to happen there, happen to this thing, because that's already there. That phase has already been kicked back into the first qubit. That phase has already been accrued by the first qubit. So already been picked up by the first qubit, and then you put another J2, the second location further away from this point, because now you're dividing by 4, get 1, and still nothing happens to the second and the third qubits. And then you apply another CR3 on the first qubit. Now you're going to divide by 8, 2 to the power 3, but that's an R3 gate. We're going to divide by 2 to the power 3, which is 1/8. So you're going to get another division by 8, and that division by 8 depends upon what the state of J3 is. Whatever the state of J3 is, nothing is going to happen to this gets 0, but an additional phase factor is going to be picked up by this relative phase by this get 1. So I'm going to be left with 0 plus EI 2 pi 0 dot J1, J2, J3 get 1, J2, J3. Right, you get a question?
So we have applied the Hadamard gate in the first step. So how is it picking up the phase? Hadamard gates are supposed to pick up the phase?
No, they're not supposed, but up till this point. So why do we have this? So what does the Hadamard gate do? It takes ket 0 and converts it to 0 plus 1 over under root 2, takes ket 1 and converts it into its orthogonal state. This phase really does depend upon what the initial state is, right? So it does add a phase. Otherwise, it's not really interesting. Okay? So this is what's going to happen to the first qubit. And then from this point onwards, nothing is going to happen to the first qubit, right? Because that channel is just going straight on, right till the end. Now the action comes at the second qubit. The second qubit, you first apply a Hadamard gate. So you would like to apply a Hadamard gate. What kind of notation am I using? UH2. So now you apply Hadamard gate onto the second qubit. And we're going to do that. Nothing happens to the first qubit. 0.J1. Now you understand the power of this notation. This notation is just for our conceptual convenience, by the way. Really, it's all about numbers. Real numbers that are being divided and multiplied and so on. So now J2 is going to change. Another 1/2 factor is going to be picked up. So I have 1/4 here now. I'm going to get 0 plus exactly in the same fashion EI 2 pi 0 dot with J2 J3 sorry. So after the Hadamard, sorry, after the Hadamard is J2 cat 1 and the third qubit still in the state cat J3. Now I'm going to apply a controlled R2 rotation on the second qubit. Now that second qubit is controlled by the third qubit and it's an R2 rotation. So J1, J2. So you divide by 2 is about 2, divide by 4. So exactly in an analogous fashion, you can just work this out. This is really straightforward now. Nothing happens to the first qubit. Get 0 plus EI 2 pi 0 dot J2. Since I am dividing by 4, that appears at the second location after this point. 0 dot J2, J3, get 1, J3. And that's it. And then you apply the final Hadamard gate on the third qubit. So overall, what the result is going to look like is the following: U, H3, 1 over under root 8, which is 2 to the power 3. J1, J2, J3, get 1. Get 1.
Second last statement J3 से मेरे change से product
डालना चाहो तो डालो, कोई मसला नहीं, जरूरी नहीं डालना वैसे, ठीक है? It's understood. So this is the final output. Does that circuit implement the quantum Fourier transform? Can you compare it with the one that we have at the top? Do they look comparable, or is there some stark difference that you notice? First of all, are they the same? So the n is equal to 3 now. Compare this and with that thing over there. Are they the same or different? They are different in the sense that the first should be the third should be the first. Okay? So you've gotten the correct phases, but the ordering of the qubits has reversed. So if after this circuit, you are able to implement another gate that swaps the first and the third qubit, you'll be done. You would have implemented the quantum Fourier transform. So Now you could swap the first and the third qubit. There are different symbols for that. This is a common symbol. Swap the first and the third qubit. Leave the second qubit unchanged. So all of this is now going to implement UQ. All of it. So at the end you will have to do a final swapping. If you have more qubits, the first and the last qubit are interchanged, the second and the second last qubit are interchanged, the third and the third last qubit are interchanged, and so on. If you have even number of qubits, that's what you do. If you have odd number of qubits, you still follow the same sequence and leave the middle line unchanged. So all of this, is this a unitary gate?
Yes.
Unitary?
Yes. Yes. Sir.
Yes. Unitary, yes. All of these gates are unitary. Is swap gate unitary?
No.
Okay, can you please write down the matrix for a swap gate? Suppose you are just swapping two qubits. You just have two qubits and you're swapping the qubits. What would the matrix look like? It's not a NOT gate. So I would like to write a 4 by 4 matrix for a swap gate. So I like write down what the matrix looks like. It's always nice to come with the truth table if you're finding difficulty in writing down the matrix.
Truth table भी नहीं है. Swap का कैसे कुछ truth table होगा भी समझ नहीं आता.
Write down the truth table. So, apically, has anyone done this? First of all, it's going to be a 4 by 4 matrix. You have two qubits. Very nice. So just to give you a hint, and this is some practice of writing down matrices. This state remains unchanged. It's an eigenstate of the swap gate. This state changes.
Exclusive or
This state also changes, where this state is another eigenstate of the swap gate. Doesn't change. Okay. So now just to take the output from the first in the sequence and write down its vector form. You take the output from the second kind of input and write its matrix vector form, and so on. This is a unitary gate. You take the transpose of this; it's already real. You take the transpose of this, apply it again, you get back to this. So this is a unitary gate. And there are ways to implement this. So, this is, I think, a homework problem in the second assignment, that one manner in which this can be implemented is through a control NOT gate, followed by another control NOT gate, followed by yet another third control NOT gate. There's a simple logic. So this is a unitary. And you multiply the three matrices together for these control NOT gates, you end up with the swap gate up to some arbitrary global phase vector. So the quantum Fourier transform is really implemented by sequence of rotations and Hadamard gates. So I can extend this to larger number of qubits as well, and you can draw the circuit for that, and you can also look this up in some textbook, what the circuit looks like, and you can even write a matrix for this. You already know what the matrix looks like for a quantum Fourier transform with remember all the omegas in there. that matrix represents this thing, including the swap gate. Should come up with some computer software like Qiskit or Mathematica in which you could try all of this out. It's very important, and I think one of the homework problems is going to focus just on the computation bit. So this is how to implement the quantum Fourier transform. By the way, it's very difficult to implement this in practice because of multiple reasons, large number of gates. So the number of gates that are required. So if I have n qubits, the first qubit uses one Hadamard gate, and for the 3-qubit case it has two controlled rotations, two controlled rotation gates. For n qubits it will have n minus 1 controlled rotation gates. So the first qubit sees n gates. The second qubit sees one less gate, right? This is one, so this has 3, this has 2. Still has a Hadamard, but one less controlled rotation, right? Finally, the third qubit has n minus 2 gates. The nth qubit has just one gate. Okay. So now you add up all of this. The number of gates that are required is just I think an arithmetic sequence. You get n into n plus 1 over 2. So the number of gates that are required, the number of operations that are required to implement a quantum Fourier transform for n qubits is n squared, small n squared. Classical Fourier transforms, if you forget about the FFT for a minute, the fast version of the classical Fourier transform, which is called the fast Fourier transform, forget about that for a minute, that does some improvement. Classically, as I mentioned in the other lecture, you need capital N square gates, which is n is 2 raised power n. So this is 2 raised power 2n. You need an x. So the kind of savings that you are getting is from exponential you go to polynomial. The quantum is giving you exponential advantage over the classical resources required. This is just computing in terms of the number of gates or operations that are required. Not talking about time complexity and so on. These gates might be really hard to implement because as you make bigger and bigger circuits for larger number of qubits, you will have R2, R3, R4, R5, which is rotation with smaller and smaller amounts. So if you have R5, so this means you have a rotation by 2 pi over 2 raised to power 5, which is 32. Really small rotation. This is 180 degrees, 360 degrees divided by 32. What's that? 5 or 6 degrees or something of that kind. So you need to make a rotation, a control rotation by 5 degrees on a single qubit. That's really difficult to do it accurately. You might hit the noise limit. So generally when you talk about Fourier transforms, you just want to ignore all of the gates that are smaller than some threshold, because they will just add to the noise. They don't, difficult to implement. You cannot achieve accuracy there. So you have an approximate quantum Fourier transform in which say after R is equal to R4, I just ignore all the gates. Okay, so then it becomes an approximation. So in real implementations, you can come up with approximate Fourier transform. By the way, this is so difficult, and this was one of the crowning achievements of quantum computing, that with the help of quantum Fourier transform and phase estimation and then factoring, you could find the prime factors of a large number. The world record so far, I think, is just factorizing the number 21. So that's the world record. So it's very difficult to implement this technologically. And there's a barrier which is called the quantum ascendancy limit. You need to have error-free quantum computation of something over 100 qubits to do something really, really fantastic. It's going to strip away all barriers and really make success. So anyway, this is the quantum Fourier transform. So in the next lecture, what I'm going to do, I'm going to start from next week. I'm going to spend just on one thing. That's factoring. That one algorithm that gave quantum computing, quantum information processing a buzz is factoring. Because our systems to do e-commerce, communicating data securely from one point to another between banks, between hospitals, between militaries, between protagonists and so on, depends upon the security of data. And since it's very hard to factorize prime factors of a large number, encryption schemes are based upon the presumption that it's really hard to do this in a polynomial amount of time. Factorization is really hard. It's an NP-hard problem in the language of quantum computer science complexity. It's an NP-hard problem. But if you had a quantum computer, you could do this in polynomial amount of time, with polynomial resources. That's why there's so much buzz about quantum information processing. So we really need to spend some time on the Shor's factoring algorithm. And quantum Fourier transform is going to be the hallmark behind all of this. So we have to do a lot of number theory to understand some discrete maths, some modular arithmetic to really understand factoring. And I will start off by one question that I would like to ask you. If I have a unitary operator, okay, just forget about it. If I have a unitary operator, and this unitary operator has some eigenvalue, some eigenvector. If this small u, ket u, is an eigenvector or an eigenstate of this unitary operator, what should I write on the other side of this equation?
So, number u is the place state.
Some number, lambda, right? And
U.
if this is a unitary operator, is there any constraint on what this number can be?
Yes.
Its magnitude should be 1. So its magnitude should be 1, which means it can always be written as ei 2 pi some angle, right? Any angle. You can always do that. So if I input this to get u, of course I get u as the output. There will be some phase factor here, this number here, lambda here, but you can't tell what the phase factor is because it's global phase. So is there a means to find out what this phase is? In other words, is there a means to find out what the thetas are? Not in this circuit, but can we come up with a circuit with some ancillary qubits so that there is some mechanism looking at the ancillary qubits perhaps and finding out what this theta is going to be? In all of the algorithms, let's look at our algorithm again. All of the algorithms face a similar scenario. They paint a similar picture. Hadamard, create superpositions, and then you do your computation. Here you're creating phases, and then at the end you would like to interfere somehow to do measurement. We haven't talked about measurement as yet, because we're just doing a quantum Fourier transform. So these output states are given over here. So they will be, first qubit will have some phase, the second qubit will have some phase, and these are the phases. Right? The first qubit has a large phase, right? Second qubit has a smaller, some fraction of this phase, then some fraction of this phase comes here. So all of these qubits are picking up some phase. So we're creating phases. But what are we doing with the quantum Fourier transform? We have to put things back through some operation and then an inverse quantum Fourier transform to do a measurement. So this is the general scheme of all quantum algorithms. You create a Hadamard superposition, equal superposition, then you sprinkle in phases, relative phases into your states, and then you do some computation and recombine in a manner that certain states are destructively interfered, certain states are constructively interfered, so you get a high probability of detecting a particular state. This is the general scheme of a quantum Fourier transform, of any quantum algorithm. For your projects, I would suggest the following. Pick up a quantum algorithm. Shor's factoring algorithm, finding the isomorphisms of groups, finding character tables, optimization, quantum machine learning. Pick up some algorithm and then try to look at it mathematically, look at the performance of the algorithm, how many steps are needed, draw the quantum circuit for this, and simulate this on a classical computer and see what the results are going to look like. And I'll send you some resources which has a compilation of many quantum algorithms. Alright, so let's meet on Monday, and hopefully the second homework is going to be uploaded in the next 24 hours as well as the solution to the first homework. Thank you.